Hello, welcome back, and we're going to be kicking off Chapter 4, which is the second law of thermodynamics. So, some things happen, some things don't happen. Gases expand to fill a vessel it occupies, but a gas that already fills a vessel doesn't suddenly contract into smaller volumes. A hot object cools to the temperature of its surroundings. A cool object does not suddenly become hotter than its surroundings. Hydrogen and oxygen combine explosively with the kick of a spark and form water. Water left on its own does not gradually decompose into hydrogen and oxygen. These everyday and commonsensical observations suggest that changes can be divided into two general categories. Spontaneous change is a change that has a tendency to occur without work having to be done to bring it about. A spontaneous change has a natural tendency to occur. A non-spontaneous change is a change that can be brought about only by doing work. A non-spontaneous change has no natural tendency to occur. Non-spontaneous changes can be made to occur by doing work. Gases can be compressed into smaller volume by pushing it in a piston. Temperature of a cool object can be raised by forcing an electric current through a heater attached to it. Water can be decomposed by the passage of an electric current. However, in each case, we need to act in some way on the system to bring about the non-spontaneous change. There must be some feature of the world that accounts for this distinction between these two types of changes. Throughout the chapter, we will use the terms spontaneous and non-spontaneous in their thermodynamic sense. That is, we use them to signify that a change does or does not have a natural tendency to occur. In thermodynamics, the term spontaneous has nothing to do with speed. Some spontaneous changes are very fast, such as the precipitation reaction that occurs when solution of sodium chloride and silver nitrate are mixed. However, some spontaneous changes are so slow that there may be no observable change even after millions of years. For example, although the decomposition of benzene into carbon and hydrogen is spontaneous, it does not occur at a measurable rate under normal conditions. And benzene is a common laboratory commodity with a shelf life of, in principle, millions of years. Thermodynamics deals with a tendency to change. It is silent on the rate at which the tendency is realized. So, to do a quick touch of review, if I'm drawing a reaction diagram and I have energy on the y-axis and we have reaction progress on the x-axis, and we're starting with our reactants at this point on the with 0 at the reaction, the beginning of the reaction, and we have the super simple version of a reaction progress. We know that we start with a reactant, we end with a product, and we have to go through some kind of high energy transition state in the absence of an intermediate, which might complicate this diagram. To distinguish between processes of spontaneous, non-spontaneous, and things that are determining rate. Let me grab a different color here really fast. We have two different deltas that help us determine this. When we're talking about spontaneity and non-spontaneity, we're looking at the delta between our reactant and our product. That will solely determine whether or not a reaction is favorable. In this case, we're going from a relatively high energy to a relatively low energy in the product. Therefore, we would be looking at a spontaneous process in this diagram because things in all aspects of nature tend towards lower energy / higher stability. However, rate is determined by the delta between the reactant and the energy in the transition state, because this is the amount of energy that needs to be overcome to elicit this downhill run from the transition state to the product. And that delta determines the rate of reaction. So this is our rate. This is our spontaneity. So with that in mind, let's talk about entropy. Entropy. A few moments' thought is all that's needed to identify the reason why some changes are spontaneous and others are not. The reason is not the tendency of the system to move towards lower energy, even though that's a strong component. This point's easy to establish by identifying an example of spontaneous change in which there's no change in energy. The isothermal expansion of a perfect gas into a vacuum is spontaneous, but the total energy of the gas does not change because the molecules continue to travel at the same average speed and so keep their same total kinetic energy. Even in a process in which the energy of a system does decrease, as in the spontaneous cooling of a block of hot metal, the first law requires the total energy of the system and surroundings to be constant. Therefore, in this case, the energy of another part of the world must increase if the energy decreases in the part of that interests us. For instance, a hot block of metal in contact with a cool block cools and loses in energy. However, the second block becomes warmer and increases in energy. It's equally valid to say that the second block moves spontaneously to a higher energy as it is to say that the first block has a tendency to go to a lower energy. So, the direction of spontaneous change. We shall now show that the apparent driving force of spontaneous change is the tendency of energy and matter to become disordered. For example, the molecules of gas may all be in one region of a container initially, but their ceaseless disorderly motion ensures they spread rapidly throughout the entire volume of the container, as we see in figure 4.1. Because their motion is so disorderly, there is a negligibly small probability that all of the molecules will find their way back simultaneously into the region of the container they occupied initially. In this instance, the natural direction of change corresponds to the dispersal of matter. A similar explanation accounts for spontaneous cooling, but now we need to consider the dispersal of energy rather than that of matter. In a block of hot metal, the atoms are oscillating vigorously, and the hotter the block, the more vigorous their motion. The cooler the surroundings also consist of oscillating atoms, but their motion is less vigorous. The vigorously oscillating atoms of the hot block jostle their neighbors in the surroundings, and the energy of the atoms in the block is handed on to the atoms in the surroundings, as we see in figure 4.2. The process continues until the vigor with which the atoms in the system are oscillating has fallen to that of the surroundings. The opposite flow of energy is very unlikely. It's highly improbable that there will be a net flow of energy into the system as a result of jostling from less vigorously oscillating molecules in the surroundings. In this case, the natural direction of change corresponds to the dispersal of energy. The tendency towards dispersal of energy also explains the fact that despite numerous attempts, it's proven impossible to construct an engine, like that shown in 4.3, in which heat, perhaps from the combustion of a fuel, is drawn from a hot reservoir and completely converted into work, such as the work of moving an automobile. An actual heat engine, all actual heat engines, have both a hot region, the source, and a cold region, the sink, and it has been found that some energy must be discarded into the cold sink as heat and not used to do work. In molecular terms, only some of the energy stored in the atoms and molecules of the hot source can be used to do work and transferred to the surroundings in an orderly way. For the engine to do work, some energy must be transferred to the cold sink as heat, to stimulate disorderly motion of its atoms and molecules. In summary, we've identified two basic types of spontaneous physical processes. 1, matters tend to become disordered. 2, energy tends to become disordered. We must now see how these two primitive types of spontaneous physical change result in some chemical reaction being spontaneous and others not. It may seem very puzzling that collapse into disorder can account for the formation of such ordered systems as proteins and biological cells. Nevertheless, in due course, we'll see that organized structures can emerge as energy and matter disperse. We shall see, in fact, that the collapse into disorder accounts for change in all forms. So moving on, entropy and the second law of thermodynamics. The measure of disorder used in thermodynamics is called entropy, which is denoted by this capital S. Initially, we can take entropy to be a synonym for the extent of disorder, but shortly we'll see that it can be defined precisely and quantitatively measured and then applied to chemical reactions. At this point, all we need to know is that when matter and energy become disordered, the entropy increases. That being so, we can combine the two remarks above into a single statement, known as the second law of thermodynamics, which is as follows. The entropy of an isolated system tends to increase. Pretty straightforward. The isolated system may consist of a system in which we have special interests, for instance, a beaker containing reagents, and that system's surroundings. The two components jointly form a little universe in the thermodynamic sense. To make progress and turn the second law into a quantitatively useful statement, we need to define entropy precisely. We shall use the following definition of a change in entropy for a system maintained at a constant temperature, where change in entropy, delta S, equals Q divided by T. That is, the change in entropy of a substance is equal to the energy transferred as heat to it reversibly, Q, divided by the temperature at which the transfer takes place. This definition can be justified thermodynamically, but we shall confine ourselves to showing that it's plausible and then show how to use it to obtain numeric values for a range of processes. There are 3 points we need to understand about the definition in equation 4.1. The significance of the term reversible, why heat, not work, appears in the numerator, and why temperature appears in the denominator. So first, why reversible? We met the concept of reversibility in section 2.3, where we saw that it refers to the ability of an infinitesimal change in a variable to change the direction of a process. Mechanical reversibility refers to the equality of pressure acting on either side of a movable wall. Thermal reversibility, the type that we're looking at in equation 4.1, refers to the equality of temperature on either side of a thermally conducting wall. Reversible transfer of heat is smooth, careful, restrained transfer between two bodies at the same temperature. By making the transfer reversible, we ensure that there are no hot spots generated in the object that later disperse spontaneously and hence add to the entropy. So, secondly, why heat and not work in the numerator? Now, consider why heat and not work appears in 4.1. Recall that from section 2.2 that to transfer energy as heat, we make use of the disorderly motion of molecules, whereas to transfer energy as work, we make use of orderly motion. It should be plausible that the change in entropy, the change in the degree of disorder, is proportional to the energy transfer that takes place by making use of disorderly motion rather than orderly motion. And thirdly, why temperature in the denominator? The presence of the temperature in the denominator in equation 4.1 takes into account the disorder that is already present. If a given quantity of energy is transferred as heat to a hot object, one in which the atoms have a lot of disorderly thermal motion, then the additional disorder generated is less significant than if the same quantity of energy is transferred as heat to a cold object in which the atoms have less thermal motion. The difference is like sneezing in a busy street, an environment analogous to a high temperature, and sneezing in a quiet library. The relative magnitude of change is going to be higher when you move the same amount of energy into a high energy system than into a low energy system. The entropy, it can be shown, is a state function, a property with a value that depends only on the present state of the system. The entropy is a measure of the current state of disorder of the system, and how that disorder was achieved is not relevant to its current value. A sample of liquid water of mass 100 grams at 60 degrees Celsius at 98 kilopascals has exactly the same degree of molecular disorder, the same entropy, regardless of what happened to it in the past. The implication of entropy being a state function is that a change in its value when a system undergoes a change of state is independent of how the change of state is brought about. One practical application of entropy is to the discussion of the efficiencies of heat engines, refrigerators, and heat pumps, which is included in the book if that's something that you'd like to go further into, and it's included in box 4.1. Now, let's take a quick look at this brief illustration, which just does a simple calculation of entropy based on reversible heat transferred and temperature. So in this illustration, the transfer of 100 kilojoules of energy as heat to a large mass of water at 0 degrees Celsius, or 273 Kelvin, results in a change of entropy equals Q reversible divided by T, and we substitute in 100 kilojoules, or 100 times 10 to the third joules, divided by 273 Kelvin. And this gives us a value of positive 366 joules per Kelvin. We use a large mass of water in this case to ensure that the temperature of the sample does not change as heat is transferred. The same transfer at 100 degrees Celsius, or 373, results in the following: a change of entropy of 268 joules per Kelvin. This is a nice demonstration that an equivalent amount of heat transferred to a sample which has a higher initial temperature has a lower change in entropy. Now moving on to the entropy change accompanying expansion. We can often rely on intuition to judge whether the entropy increase or decrease when a substance undergoes a physical change. For instance, the entropy of a sample of gas increases as it expands because the molecules get to move in a greater volume and so have a greater degree of disorder. However, the advantage of equation 4.1 is that it lets us express the increase quantitatively and make numeric calculations. For example, as shown in derivation 4.1, which is included in the slide, it lets us express the increase. Let's see here. So, as shown in 4.1, derivation 4.1, not equation 4.1, we can use the definition to calculate the change in entropy when a perfect gas expands isothermally from volume initial to volume final, and we obtain equation 4.2, in which change in entropy equals NR, natural log of the ratio of the final volume to initial volume. So we've already stressed the importance of reading equations for their physical content. In this particular case, if the ratio of, if in this case, final volume is greater than initial volume, as in an expansion inherently, then the ratio of VF over VI has to be greater than 1. And the logarithm is inherently positive. Consequently, equation 4.2 predicts a positive value for delta S corresponding to an increase in entropy, just as we anticipate. The change in entropy is independent of the temperature at which the isothermal expansion occurs. More work is done if the temperature is high, because the external pressure must be matched to a higher value of the pressure of the gas. So more energy must be supplied as heat to maintain the temperature. The temperature in the denominator of equation 4.1 is higher, but that metaphorical sneeze in terms of that we used earlier is greater too, and the two effects effectively cancel. Here's a subtle but important point. The definition in equation 4.1 makes use of a reversible transfer of heat, and that is what we used in the derivation of equation 4.2. However, entropy is a state function, so its value is independent of the path between the initial and final states. This independence of path means that although we have used a reversible path to calculate delta S, the same value applies to an irreversible change, for instance, free expansion, between the same two states. We cannot use a reversible path to calculate delta S, but the value calculated for a reversible path applies. However, the path is traversed in practice between the specified initial and final states. You may have noticed that in self-test 1, which is also in the book, we did not specify how the expansion took place, other than that it's isothermal in nature. So let's take a look at how the entropy change accompanying heat occurs. We should expect the entropy of a sample to increase as the temperature is raised from the initial temperature to the final temperature, because the thermal disorder of a system is greater at the higher temperature when the molecules move more vigorously. To calculate the change in entropy, we go back to the definition in equation 4.1 and as shown in derivation 4.2, that find, provided the heat capacity is constant over the range of temperature of interest, very important distinction, delta S equals C, the heat capacity, times the natural log of the ratio of the final temperature to the initial temperature. So in this case, C is the heat capacity of the system. If the pressure is held constant during the heating, we use the constant pressure heat capacity, C sub P, and if the volume is held constant, we use the constant volume heat capacity, C sub V. Once more, we interpret the equation generally as follows. When the final temperature is greater than the initial temperature, inherently the ratio of final temperature to initial temperature has to be greater than 1, which implies that the logarithm must be positive. So change in entropy has to also be positive. And therefore, the entropy increases as the temperature is raised. Secondly, the higher the heat capacity of the substance, the greater the change in entropy for a given rise in temperature. A high heat capacity implies that a lot of heat is required to produce a given change in temperature. So that metaphorical sneeze must be more powerful than for when the heat capacity is low, and the entropy increase is correspondingly high. When we cannot assume that the heat capacity is constant over the temperature range of interest, which is the case for all solids at low temperatures, we have to allow for the variation of C with the temperature. The result of this is that delta S equals the area under a graph of C over T plotted against T between the initial and final temperatures. So we would be taking the integral of this relationship. To use this, we measure the heat capacity through a range of temperatures of interest and then make a list of values. Then we divide each of these by the corresponding temperature to get the ratio of the heat capacity to temperature at each temperature, and then plot these CTs against temperature and evaluate the area under the graph between the temperatures of interest. The simplest way to evaluate the area is, but it's very crude, is just count squares on graph paper. A more accurate way and the only reliable one in practice is to fit the data to a polynomial and then to use a computer to evaluate the integral. A really old technique would be to print this out, and then you actually delicately slice the integral out with a razor, and then you weigh the paper. And then you use that as a tool to determine the area under the curve. Now, in terms of rationale, I wanted to go back to this second point here. The higher the heat capacity of the substance, the greater the change of entropy. There is actually a bit of intuition to this, because heat capacity, if you recall, is an indication of how many different ways you can disperse thermal energy within a system. So if you have the ability to disperse energy as it comes in, instead of exciting atoms, that energy is dispersed. However, if you have limited ability to disperse energy, it's going to drive the temperature up faster. So because of that, there's an inherent relationship between the amount of energy in and the heat capacity and how that energy increases entropy in that particular substance. So, on to the entropy change accompanying a phase transition. So briefly, we can suspect that the entropy of a substance increases when it melts and when it boils because its molecules become more disordered as it changes from solid to liquid and from liquid to vapor. We've even discussed this thoroughly in 100-level chemistry. But let's elaborate. The transfer of energy as heat occurs reversibly when a solid is at a melting temperature. If the temperature of the surroundings is infinitesimally lower than that of the system, then the energy flows out of the system as heat and the substance freezes. If the temperature is infinitesimally higher, then energy flows into the system and as heat and the substance melts. Moreover, because the transition occurs at a constant pressure, we can identify the heat transferred per mole of substance with the enthalpy of fusion, or /melting. Therefore, the entropy of fusion, change of entropy fusion, the change of entropy per mole of substance as the melting temperature T sub F, which is denoting fusion, not final in this particular case, is as follows. At the melting temperature, change in entropy of fusion equals the change of enthalpy of fusion times the temperature of fusion divided by the temperature of fusion. Notice how we must use the enthalpy of fusion at the melting temperature to get the standard entropy of fusion. As the melting temperature, we use the melting temperature at 1 bar and the corresponding standard enthalpy of fusion at that temperature. All enthalpies of fusion are positive, so all entropies of fusion are positive too. Disorder increases on melting. The entropy of water, for example, increases when it melts because the disorderly structure of ice the orderly structure of ice collapses as the liquid forms, as we see in figure 4.7. Where on figure A, we have a nice orderly structure dictated by uniform hydrogen bonding in this crystalline solid. And in B, as it melts, we lose that order, we gain space between the molecules, and we get more ability or capacity for random motion between them. So, the entropy of other types of transitions may be discussed similarly to that of water. Thus, the entropy of vaporization, delta vape S, at the boiling temperature boiling of a liquid, is related to the enthalpy of vaporization at that temperature by the following analogous equation, where the change in enthalpy of vaporization equals the change of enthalpy of vaporization times the temperature of boiling divided by the temperature of boiling. To use this formula, we use the enthalpy of vaporization at the boiling temperature specifically. For the standard value, delta vape S, we use data corresponding to 1 bar. Because vaporization is endothermic for all substances, all entropies of vaporization are positive. The increase in entropy accompanying vaporization is in line with what we should expect when a compact liquid turns into a gas. Entropies of vaporization shed light on an empirical relation known as Troughton's rule. Troughton noticed that a change in enthalpy times the temperature of boiling divided by the temperature of boiling is approximately the same and equal to about 85 joules per mole Kelvin for all liquids except when hydrogen bonding or some other kind of specific molecular interaction is present. We know that the quantity for this term, however, is the entropy of vaporization of the liquid at its boiling point. So Troughton's rule is explained if all liquids have approximately the same entropy of vaporization at their boiling points. This near equality is to be expected because when a liquid vaporizes, the compact condensed phase changes into a widely dispersed gas that occupies approximately the same volume, whatever its identity. To a good approximation, therefore, we expect the increase in disorder and therefore the entropy of vaporization to be almost the same for all liquids at their boiling temperatures. Naturally, there's exceptions. The exceptions to Troughton's rule include liquids in which the interactions between molecules result in the liquid being less disordered than a random jumble of molecules. For instance, the high value for water implies that the water molecules are linked together in some kind of ordered structure by hydrogen bonding, with the result that the entropy change is greater when this relatively ordered liquid forms a disordered gas. The high value for mercury has a similar explanation but stems from the presence of metallic bonding in the liquid, which organizes the atoms into more definite patterns than would be the case if such bonding were absent. So in Table 4.1, we have a summary of entropies of vaporization at 1 atmosphere and the normal boiling point. And you can see that we have highly similar changes of entropy of vaporization for benzene, bromine, carbon tetrachloride, cyclohexane, etc. But for water, we have substantially higher because of hydrogen bonding and the increased order that dictates in that liquid phase. Same for mercury, and also for ammonia, we have a fairly high value also because of hydrogen bonding inherent within ammonia. So, as an example, to calculate the entropy of phase transition at a temperature other than the transition temperature, we have to do additional calculations. So let's take a look at that. So example 4.1, calculating entropy of vaporization. So in this problem, you're asked to calculate the entropy of vaporization of water at 25 degrees Celsius from thermodynamic data and its enthalpy of vaporization at its normal boiling point. So the strategy for this is the most convenient way to proceed is to perform 3 calculations. First, calculate the entropy change for heating liquid water from 25 to 100 degrees Celsius. Then use equation 4.7 and data from table 3.1 to calculate the entropy of transition at 100 degrees Celsius. Next, calculate the change in entropy for cooling the vapor from 100 degrees Celsius to 25 degrees Celsius. Finally, add the 3 contributions together. So the solution looks like this. From equation 4.3 with data for the liquid from table 2.1, we substitute in the heat capacity for liquid water and our 2 temperatures and obtain a value of 16.9 joules per Kelvin per mole. From equation 4.7 and data from table 3.1, we substitute the change of enthalpy of vaporization and the temperature boiling point of water, which is 273 in this case Kelvin, and obtain the following: 109 joules per Kelvin per mole. And then from equation 4.3 and data from table 2.1, we calculate using the specific heat of water in vapor phase and the final temperature and initial temperature, and obtain a negative 7.54 joules per Kelvin per mole. The sum of these three entropy changes is the entropy of transition at 25 degrees Celsius. So we just sum them and get a final term of 118 joules per Kelvin per mole. And this is a good place to take a break, rest everyone's brain. It's a lot of information coming in. I'm going to upload this video and then we will pick it up and finish up this chapter.